as we've seen, then the mass of our sphere is mass equals an integral of density times volume. We should understand by now in what sense this is the case, and in detail in terms of sample points and partitions, just exactly how these integrals come about. In spherical coordinates, of course, when we integrate with respect to volume, we're going to use a triple integral, and the triple integral for the mass, which we've already seen and verified, is 0 to pi, 0 to 2 pi, 0 to r of our delta function, which is the 12 minus 9 rho over big R. And then that's rho squared sine phi d rho, rho going from 0 to r, d theta, theta going from 0 to 2 pi, d phi, phi going from 0 to pi. In cylindrical coordinates, what are the limits in our integral? Well, again, we have these inequalities, which I believe we can display at the same time we write out the results. Okay, we're going to have the integral. The only restriction on the order of integration is that z needs to be integrated before r. So we're going to integrate z first, and then we'll integrate theta with respect to theta last. So we'll go from 0 to 2 pi, from 0 to big R, from negative square root of r squared minus little r squared to the square root of big R squared minus little r squared. Our density function is 12 minus 9 times the square root of r squared plus z squared over big R. And then that's going to be times our volume increment being r dr d theta dz, with again r theta and z being in fairly arbitrary order. So we first integrate with respect to z, then with respect to r, then with respect to theta. In rectangular coordinates, again, we have our inequalities, which imply an order of integration and limits on our integral. Going to be exactly the same as for a volume integral, except this time we're integrating density with respect to volume, so that the mass is the integral from negative r to r with respect to x, from negative square root of r squared minus x squared to the square root of r squared minus x squared with respect to y, and I've got those out of order. From the outside in, dx should have been last, and then the next integrals with respect to y, and the final integral will be with respect to z. We're going to go from r squared minus x squared minus y squared negative to the square root of r squared minus x squared minus y squared. And again, the inner integrals with respect to z, the next integral with respect to y, the next integral with respect to x. And I've left out my density function, so I'm going to have to go ahead and make a repair here. We'll get that in a second. Okay, the dz, dy, dx has been moved over, leaving me room to write the integral, write the density function in here. And of course, our density function is again 12 minus 9 squared of x squared plus y squared plus z squared over big R. So that's 12 minus 9 times the square root of x squared plus y squared plus z squared over big R with respect to z, with respect to y, with respect to x. What should be clear is that in this case, with the density function being a function only of rho, our integration in spherical coordinates is going to be somewhat simpler than in cylindrical, which is in turn simpler than it would be in rectangular coordinates. We have, of course, just recently seen this integral in the spherical case, and we know that we're just going to have to integrate a polynomial in rho, 12 rho squared minus 9 rho cubed over r. And then a little bit later we're going to have to integrate the sine of phi with respect to phi. Both of those are easy integrals, and there's no additional complication introduced by the limits on the integrals, which are all constant. In cylindrical coordinates, and we've seen integrals of this nature, the z integral here is going to be a little more complicated. We're going to have to use the substitution z equals r times the sine of theta, and all the implications of that. We'll end up having to integrate essentially a sine squared function and then back substitute. We've seen how that works, and we're going to have to do the same thing here, but we're going to have to do it twice, one for the z integral and again for the y integral, and it's going to be a little more complicated, not beyond our ability, but simply a little bit more of a pain than would be the integral in this case. Now we could ask what happens if we want to calculate moment of inertia. Now that is an integral of what? Now that's an integral of, write this in an order that makes sense in terms of moment of inertia. Of course, we're going to change the order when we do the integral. This is our mass, our delta density function times our volume increment, and then that's times, I'm not going to write r squared because that would be really easy to confuse, as we've seen with the polar coordinate r. So I'm going to say times the radius squared, where the radius is actually the distance from the axis to our volume increment. And we're going to see how these would be written in spherical, cylindrical, and rectangular coordinates.